Good morning. Thank you for the lovely introduction, and thank you all for being here today. This talk is going to need two people, so let me introduce you to Helen Nissenbaum, a philosopher who works on philosophical issues that arise in the context of new technologies. And Helen's early work on the question of privacy in public, say when there are surveillance cameras and all kinds of ways in which our actions are tracked, what does privacy mean in that setting? For simplicity, in this talk, we're going to focus on a scenario in which one or more data analysts interacts with a database. So assume that the database is filled with sort of useful but highly sensitive information from a collection of individuals that are drawn from an underlying population. And the goal is to learn about the population without learning too much about any individual in the data set. So maintaining the privacy of the individuals in the data set. So there are lots and lots of motivating scenarios for this. Our initial work was motivated by the census, since privacy of census data is legally mandated. But there are really zillions of applications from the allocation of resources, which is really what census is supposed to be all about, to epidemic detection based on over-the-counter drug purchases, analysis of loan application data for evidence of systematic discrimination, and so on. And this is a problem that is more than 50 years old. It shows up at least in 1965, perhaps earlier. Now, the first thing that you might think of is de-identification. And in de-identification, we have a database, and somehow or other there's some magic process that is applied to the database, and what is released is a so-called de-identified data set. And the only thing I have to say about this is that de-identified data isn't. Either it isn't de-identified, or it isn't data anymore. And there are a host of results that support this conclusion, and I'm not going to talk about this approach any further in this talk. Now, you might say, what happens if we just release statistics? So you have an intuition that a statistic is not compromising of privacy. So for example, suppose I said, how many people in this room have the sickle cell trait, and we got the answer to that, you would probably feel that everybody's privacy is protected because there's so much uncertainty as to sort of, if the answer, say, is one person or two people, as to who those two people are. And there is something to that, but it's not enough. So I call this the statistics masquerade. Let's consider a very simple attack called the differencing attack. Differencing attack is a pair of queries. Say, how many members in the House of Representatives has the sickle cell trait? So again, large set of people. You have a question? Oh, large set of people. If the answer, whatever the answer is, you feel that it's protecting the privacy of each individual. But if we follow up with a second question, which is how many people in the House of Representatives other than the Speaker of the House have the sickle cell trait? Again, by itself, that seems like a very benign statistic. But with the two of these together, with exact answers to the two of these together, you can deduce the sickle cell status of the Speaker of the House. And this is sort of a special case of what I like to refer to as the Big Bang attack. It's also called the Dinora-Nissim attack in honor of the first two people who demonstrated this sort of attack, or sometimes a Dini attack. And I don't have time to go into what this attack is. There's a whole class of attacks that have a similar flavor that show, sort of even stronger or more surprising impossibility results here. But I do like to summarize this as the fundamental law of information recovery. So the fundamental law of information recovery tells us that whatever you think privacy might be, overly accurate estimates of too many statistics is blatantly non-private. Whatever you thought privacy was, overly accurate estimates to too many statistics will destroy it. Okay. And I just want to give one really nice example of an attack that is purely statistical in nature. So this was described in a work of Homer et al. In 2008. So suppose for the moment that we are single-strand DNA individuals. Okay. So each person is represented by a string of C, T, Gs, and As, and everybody's DNA agrees in most places, but there are certain locations called SNPs, for single nucleotide polymorphism, in which there is some variation among the population. Maybe 94% of the population has what's called the major allele, the more popular variant, say C, and 6% maybe will have the less popular variant or the minor allele. And what Homer et al. Showed is that given, say, my DNA from this cup, suppose we have a study, and this study was of people that have been diagnosed with a certain illness. And we have a bunch of people in the case group, those are the people that are diagnosed, and we have a bunch of people who are in a control group, who are healthy. And in the genome-wide association study, in its simplest form, they look at SNPs, and they're looking for places where the allele frequencies in the case group are very different from the allele frequencies in the healthy population, in order to see whether there is, in fact, an association between this SNP and the disease. And the attack says, given my DNA and given the population, the statistics for the healthy group and the case group, it's, at least in theory, possible to determine whether I'm a member of the case group. And I've overstated the case slightly, but that's the gist of it. Now, it's true that looking at my DNA, you might be able to tell that I was susceptible to a certain illness, but that's different than having been diagnosed with it. And as a result, the National Institutes of Health revised their policies regarding access to the statistics for these sorts of studies. Okay. Now, in the modern age, things are even worse because information from various sources flows and combines in very surprising ways. And each one of these pictures represents sort of a known attack from the literature, either the technical literature or the popular press. So LaTanya Sweeney said, "Computer science got us into this mess. Can computer science get us out of it?" So that's what we want to see. We're interested now in some kind of privacy-preserving data analysis. So we want to use computer science, we want to use math, we need a formal definition of what privacy is. What does it mean to protect privacy? So here we have our data set, and we have Helen in the data set. And the question that we're asking is, what kind of privacy should we be offering to Helen? What are the guarantees that we want to give her? I'm missing a slide, so I'll have to tell you. So the first thing that you might try is to say, you shouldn't learn anything new about Helen. That is, you might know all kinds of things because she's a famous researcher, she has a blog, a website, she has published papers. There's a lot that's known about her. What you'd like to say, perhaps, is that the data analyst interacting with the data set shouldn't learn anything beyond what is learnable without that data set. And that is, in fact, a nice analogy to semantic security for crypto systems, and it was articulated in the statistics community as a desideratum 5 years before the development of semantic security in 1977 by Tordellinius. And the problem here is that, in some sense, what is the point? In other words, suppose I'm from Mars and I believe that all humans have 2 left feet. And by interacting with the data set, I learn that the vast majority, so I think that Helen has 2 left feet, and I learn that the vast majority of all humans have 1 left and 1 right foot. So now I've learned something about Helen because I've learned something about humans. And the question is, have I compromised Helen's privacy? So here's a sense in which we did not. I would have learned the same things had Helen been replaced by another random member of the population in the data set. If she's no longer in the data set, it doesn't feel quite right to accuse this data analysis process of compromising her privacy. And we adopt that definition. So ideally, we're going to learn the same things if Helen's replaced by another random member of the population, and in that case, we'll say privacy is not compromised. Now, this property is also known as stability. That is, you learn the same things independent of small perturbations in the data set. And for those of you who are knowledgeable about machine learning, you know that stability is a very valuable property, and we'll see that in a minute. So differential privacy requires, in English, that the outcome of any analysis is essentially equally likely, independent of whether any individual joins or refrains from joining the data set. So Helen goes away, LaTanya joins, Helen's replaced by LaTanya. The same things should be learned in all of these cases. So that's a fine definition of privacy, but we're also interested in data analysis. We don't want to just have trivial conclusions that we could have learned without any people whatsoever. And here's just a hint as to why something is going to be possible here. From the machine learning community, we know that stability prevents overfitting. So stability not only preserves Helen's privacy, but it also preserves overfitting. In other words, privacy and generalizability are actually aligned. We're so used to hearing about these trade-offs between privacy and utility, and it's true, there is a trade-off. But there is also some sense in which these two goals are aligned. Now here's the formal definition of differential privacy, which is joint work with McSherry, Nissim, and Smith. And for now, just take delta to be 0. Delta is always very small, and I should have left it off the slide, but anyway, for now, just assume delta is 0. So we say, before I can really interpret the definition for you, I have to tell you what all the pieces are. So we have algorithms. They work on data sets. They produce outputs from a space of outputs, okay? A range. Now, our algorithms are going to be randomized. So when we have any given data set, we don't have a unique element in the range that we get mapped to, but rather we get mapped to a probability distribution over the range. Next, we need the notion of adjacent data sets, or data sets that differ in just one element. And those are the data sets that we've been talking about. We have the data set with Helen, we have the data set without. Those two data sets differ in just one element, that is Helen. So in adjacent data sets, one is a subset of the other, and the larger one has the data of just one more person. So we say now that M gives our algorithm, our mechanism M, gives epsilon differential privacy if for all pairs of adjacent data sets, X and Y, and every event, every possible subset of outputs, the probability of this event when the database is X is at most e to the epsilon times the probability of the same event when the database is the neighboring database Y. And for now, we're taking delta to be 0. So this bounds the ratio. When delta is 0, we're bounding the ratio of these two probabilities by e to the epsilon. Our probability space is over the randomness that's introduced by the algorithm. So we are not talking about probabilities over the draws that created the database in the first place. In some sense, as algorithm designers, we have no control really over the sampling process, but we do have control over the algorithm. So this is the right probability space. The coin flips are under the control of the good guys. Okay. Now, it's not possible to know the probability of a bad event. So what's a bad event? A bad event is that the police department does some analysis of the power consumption statistics for my community and comes and busts me for grow lights, having grow lights. That's a bad event from my point of view. It's impossible to understand what the probability is of that. The police have to think of it, I don't know, whatever. And in general, when people propose methods of protecting privacy and you say, well, what if such and such happens? What if somebody cross-links the data set, the anonymized data set with this other data set? What if somebody happens to know my DNA? And they say, well, that's very unlikely. Now, they have no idea what they're talking about. When they say unlikely, they have no probability space. So, it is impossible to know the probability of bad events, but what differential privacy does is it controls the way in which my probability of having a bad event changes as a result to joining the data, as a result of my joining the data set. Okay. And we call epsilon our measure of privacy loss. So here are some properties of differential privacy. First, it's immune to auxiliary information. So for all of you who have heard about the Netflix prize training data attack, differentially private methods would have prevented that. If you've heard about the identification of the medical records of William Weld by LaTanya Sweeney in 1997, differential privacy would have prevented that. If an algorithm is differentially private, it's differentially private no matter what an adversary happens to know. Differential privacy is a property only of the algorithm and not of anybody else's knowledge. So not only does it protect against arbitrary auxiliary information that people have now, but it also protects against arbitrary extra information that they'll get in the future. We have a concrete measure of privacy loss that is more nuanced and more powerful than a single yes, it's private, no, it isn't bit. So because of that, we can actually do things like understand cumulative privacy loss under composition, under multiple epsilon differentially private mechanisms. In the very worst case, the epsilons and the deltas add up, but we can actually do a little bit better than that. And it also automatically ensures group privacy. So if an algorithm is epsilon differentially private for an individual, and you're worried about your family of size 5, it will be 5 epsilon differentially private for your family automatically. And finally, because we are computer scientists, differential privacy is programmable. That is, because we have these composition theorems that tell us how privacy loss adds up, we can now start designing algorithms that are differentially private for complicated statistical analyses based on some very simple differentially private primitives. In other words, we can program using these blocks. And indeed, there are some programming platforms, such as Pink and Iravad, that do allow actual programming with differentially private primitives. So I'm going to describe just one of many techniques. This is a very popular primitive, the addition of symmetric noise. So suppose we want to compute a real valued function of our data set. So our database is those blue points, and the star is f of the database, f of x, and we would like to compute this and release it in a differentially private way. Now, we have to worry about the behavior of the function f on adjacent data sets. So, for example, if I add this yellow point and I get a new database y, I have now pulled f of x to f of y. We've pulled the answer, what the output, the exact answer should be. So intuitively, what we want to do is we want to add random noise to obscure the difference between f of x and f of y. So for example, if this is a probability distribution on outputs when the database is x, this might be the probability distribution on outputs when the database is y. And as long as for every possible output, the ratio of these probabilities is bounded, we'll have differential privacy. So informally, to achieve epsilon 0 differential privacy, we're going to add symmetric noise that is scaled, that has, let's say, standard deviation, roughly, the sensitivity of the function, which I'll define in a second, divided by epsilon. So the sensitivity of the function is the worst case the maximum over all pairs of adjacent data sets of the amount by which one person's data can swing the answer. This is the thing that we have to hide. We have to hide the addition of somebody whose data swings the value of the function that much. We have to hide it always. So let's just look at the shape of this. In the numerator, we have the sensitivity. Bigger sensitivity means we need kind of wider scaled noise. In the denominator, we have the privacy. An epsilon of 0 is perfect privacy. And in general, smaller epsilon is better privacy. So we have epsilon in the denominator where it should be. If we make it smaller, we have wider noise. Okay? Notice also that the noise depends only on the function f and on the desired privacy epsilon. The actual data set is completely irrelevant. So it's perfectly fine to publish the distribution from which the noise is being drawn without compromising the privacy at all. It would be the same no matter who was in the data set. Formally, if we use the Laplace distribution, as described here, then we get epsilon 0 differential privacy. So again, this is just one primitive for differential privacy. And we can handle multiple queries via the composition bounds. So this is the more complicated form of the composition theorem. I had said originally that in the worst case, all the deltas and the epsilons add up. So suppose I'm composing k different differentially private mechanisms. This theorem lets us sort of scale things to square root of k rather than k, so that's a big savings. Okay. And finally, I just want to quickly mention another little primitive which we're going to use in the next part of the talk, which is report noisy argmax. So I have a bunch of values, and I want to know the index of the largest value or the smallest value, it doesn't matter. I don't want to know the value, I just want to know its index. So it's enough to add noise that is scaled just to the sensitivity of any one of these values divided by epsilon. I don't need to do the whole set at once. And then report only the argmax. Okay, don't reveal any of the values. Now, there is a very rich algorithmic literature on differentially private algorithms, and the next session, or rather, I think at least 3 of the next sessions will have differentially private algorithms described in them. And there's also a book that Aaron Roth and I have written, which is available legally and for free on the web, The Algorithmic Foundations of Differential Privacy. Okay, so I'd like to talk a little bit about some new work on false discovery control. This is with Wei-Jiasu and Li Zhang. Now, here's a brief introduction to hypothesis testing. Let me introduce you to the null hypothesis. The null hypothesis basically says there is no effect. That is to say, you might be trying to test whether a drug increases life expectancy, and the null hypothesis says no, it does not affect life expectancy. And in the context of the genome-wide association study that I mentioned earlier, the null hypothesis is that the SNP is not associated with the disease. Now, the game is, when can we reject the null hypothesis? So we reject the hypothesis that nothing interesting is going on and conclude that something interesting might be going on. Okay. So the problem here is to distinguish sort of random effects that come from the sampling procedure that created your data set from the true effects, which is, say, that the drug does affect life expectancy. And the statisticians have introduced what's called the p-value, which is the likelihood of an observation this extreme or more extreme under the null hypothesis. So if something is extremely unlikely under the null hypothesis, you say, okay, we'll go ahead and reject the null hypothesis and decide maybe something interesting is going on. And often you assume that the true nulls are uniformly, or it's defined so that the true nulls are uniformly distributed in 0, 1. And so then there's this question of how small is small enough. And you've probably all heard of, cutoff values of 0.05 or 0.01. But we all know that when you have lots and lots of tests, because of these random effects, even if all of the nulls are true, nothing interesting at all is going on, you're going to return, a 0.01 fraction as being interesting, as rejected. So one way that people cope with this is just by being very, very much more demanding. If you're doing a test of M hypotheses, you divide your cutoff point by M. But that tends to kill a lot of the things that you're interested in and that you really would like. So Bignamini and Hochberg sort of defined a change of the goal, which is instead of trying to ensure that there is no false discovery with significant probability, you want to control the false discovery rate. So you want that the false discoveries divided by the total number of discoveries should be bounded by some number. And the expectation here is going to be over the sampling. So here is what they did, and I'll describe their algorithm, which is very simple, and I'll give my intuition, which I am so not an expert on this topic, so if it turns out that my intuition is radically wrong, could somebody please tell me after the talk? Or maybe spare the audience and tell all of them. But, so we're going to have this desired controlled rate of Q. So we take the p-values and we sort them. So P of 1 is the smallest one, P of M is the largest one. And we define certain cutoff values where the jth cutoff is Q over M times J. Q is our rate that we want, M is our total number of hypotheses, and we multiply this by J. So here I have a picture, and here's the algorithm. Starting at the right side, so for M equals 1, for J is equal to 1, starting with P of M, you compare the jth p-value to the jth cutoff, and if it is less than the cutoff, you reject, that is, you say might be interesting, all of the p-values to the left, all of the hypotheses corresponding to p-values, to the jth smallest p-values. Okay? But if it turns out that you're over the threshold, then move on to j minus 1 and continue. So you're going to work your way down until you get to a certain point where you're under the threshold, and then you're going to take everything else to the left. For reasons that are completely beyond me, this is called the step-up procedure. And again, if anybody can tell me why that's the case, I'd be grateful. Okay, so this is what the algorithm does. It walks down until it finds this cutoff point that's satisfied, and then it takes everything else. Now, the intuition is, suppose all of the nulls were true. Then, remember, they're uniformly distributed between 0 and 1. So you would expect J over M times Q p-values in the range between 0 and J over M times Q. So if instead you find J of them, which is exactly what you're testing for in this condition, then intuitively only a Q fraction of them should be bad and the rest are good. It's just intuition. Now, suppose we wanted to carry this algorithm out in a privacy-preserving way. Here's the algorithm, and here's the first thing that we're going to try. I told you about that report noisy max primitive. Find the index of the guy with the biggest value. So we're going to try to do exactly that. We will iterate using report noisy max on the p-values. Now, the first problem is, suppose when we say look at P of M, we find it is not less than the threshold. So we gained absolutely nothing in terms of finding interesting hypotheses, but we've done some algorithm, we've carried out some algorithm, and we've used up some privacy. So we're paying sort of for the bad stuff, and we pay for all the bad stuff until we find a good point, and then we're done. So instead, we'll start from the left. We'll start with the smallest p-value, and again, we'll do this procedure. Now, again, for reasons that are not clear to me, even though we're going up in p-values, this is called the step-down procedure. And this is well studied, though, and it apparently also has power that's comparable to the other one, to the one where you start at the right. But now, every time we run the report noisy min algorithm, and we pay for it, either we're done with the algorithm or we get something to reject. We get a good thing. So now we're only paying for the good stuff. Now, that's the idea for the algorithm. So we're going to iterate now for just some number k of steps. So we're fixing in advance an upper bound on the number of hypotheses we're going to reject. And we're going to do this report noisy min of the p-values. And possibly, yeah, okay. And we may be more aggressive in our thresholding in order to compensate for the fact that there's noise in these values. Now, why is this reasonable? Why is it reasonable to say, well, I'm only going to look for k of them? And the context here is, you may have huge numbers of hypotheses, for example, in the GWAS case. And there may only be time or money to follow up on a smaller number. I mean, typically there is only time or money to follow up on a smaller number of rejected hypotheses for further investigation. So we're going to say we're going to settle for some number k, and that will be an input to our algorithm. Now, there are some technicalities because of the sensitivity of p-values, so we have to play some games. Not very interesting. Okay. Now, and here's something interesting that did come out of this, which is a better understanding of what can be done, or a better analysis, perhaps, of the Bignamini-Hochberg algorithms. So the traditional Bignamini-Hochberg algorithms had the property, as you saw in the picture, where all of the rejected hypotheses are sequential. Like, you start at the, they occupy some range at the left side of the picture. So you're rejecting the R smallest for some value of R. In the differentially private version, we're going to be adding noise to the p-values. We can't look at them directly. And there will be some, when we do report noisy min, well, maybe we'll get the min, maybe we'll get something that's, the fifth smallest this time, and next time the third smallest, and the following time the seventh smallest. So things are sort of coming out of order. You're only rejecting things that have approximately the smallest counts, not the actual R smallest counts. Also, because we've added noise, the distribution now on the noisy p-values of the nulls is no longer uniform. And so we need somehow a more robust proof of controlling the false discovery rate. And we get a proof that is more robust, and that when we get a proof when we're even ignoring privacy of a more robust version of BHQ. In particular, we require fewer independence assumptions than seem to be required anywhere else in the very large literature on this topic. So this is something that we came to by approaching this from differential privacy. It's not a result about this part of it is not a result about differential privacy, but that's a byproduct. Now, it's not entirely for free yet. So for example, the original algorithm controls the false discovery rate at Q. We're controlling it at some value of C times Q plus Q log 1 over Q, where C is some absolute constant that's, I think, about 6. We can get rid of the Q log 1 over Q term if we look at the case where we have at least 2 false erroneous rejections. the number of false discoveries. And we get some other, we get a nicer behavior when we look at a different kind of measure where we, for the case where we're rejecting at least 2, but they're not necessarily false rejections. Okay. So again, and what I should have mentioned is these are results for the non-private case, and we relate our results for the private version to the relates of the non-private one via some slightly more aggressive thresholding. But we get essentially the same behavior with very high probability. Okay. So that was some work which, because we were going at things from differential privacy, we learned things that we didn't know before about a very well-studied field. Here's now a result where we are actually using differential privacy itself and going somewhere where we were not able to go before, but we're crucially using the differential privacy. So in the last couple of minutes, I'll talk about differential privacy in adaptive data analysis, or correctness prediction. So as we've been discussing, there are a lot of efforts to control the false discovery rate. And we were just talking about the Bignamini-Hochberg procedure and its variants. But there are also sophisticated cross-validation techniques and use of holdout sets and so on. Now, most of the theory is for the static case in which the hypotheses have been fixed in advance. The hypotheses have been fixed in advance, or what you're going to do with the data set has been fixed in advance. But as Tukey said, we often forget how science and engineering function. Ideas come from previous exploration more often than from lightning strokes. So in practice, science is an adaptive process. The second question that we ask of the data set depends on the answer to the first question. The third study depends perhaps on the first and second studies. Moreover, things are going to get worse in the sense that it used to be that perhaps if you saw a study that inspired you, you'd go out and you'd create new data for your study and you'd do a follow-up study on the new data. But now people will be working with massive data sets and everybody will be studying the same data sets. It might be all of the query logs or something like that. It's not reasonable or rational to think about going out and recruiting a new data set. People will be doing multiple studies on the same data set, and the new studies will be inspired by the results of the previous studies. So in this land of large data sets, we have an accuracy problem. In our formulation, remember, we have a scenario where we have an analyst that's asking questions and getting answers. In our formulation, we have that the ith query depends on the answers to the first I-1 queries. And the worry is that the analyst is going to find a query for which the database is not representative of the population from which it is drawn. In other words, she will overfit. And she will report a surprising discovery, and we'll have another false discovery in science. So the key claim, which is joint work with Feldman, Hart, Patassi, Reingold, and Roth, is that differential privacy neutralizes the risks that are incurred by adaptivity. That is to say, it's not doing anything for the static case by itself, but it does neutralize the other risks that come from adapting. So in particular, what we show is that it is hard to find a query, for which the database is not representative. So let me just try to give you a little bit of intuition why that's the right thing to think about. Let's fix a particular query, say what fraction of the population is over 6 feet tall. All right. Suppose I've gone out and I've recruited a data set using very good sampling procedures so that it's a representative data set. And it's a large data set. So you all know that if the data set is sufficiently large, then it will, with very, very high probability over the sampling procedure, give an answer that is approximately correct for the population as a whole. Okay? So the way that I would describe this is most data sets are representative with respect to this query. Query is chosen independent of the data set. Draw a data set to answer your question. It's very likely to be representative, and the answer you get will be a good one for the population as a whole. Great. So now suppose that in the course of the analysis, the adaptive analysis or exploration of the data, the analyst finds a query for which the data set is not representative. Then, intuitively, she has actually learned something significant about the data set with no knowledge of the data set. In fact, if the data set hasn't even been drawn, she's definitely not going to be finding queries that are not representative. So she must have gleaned something about the data set. I mean, she may not realize it, but she must have gleaned something about the data set that caused her to come up with this overfitted query. So on an intuitive level, preserving the privacy of the data may prevent overfitting, and that's exactly what we show to be the case. So a couple of comments about this. There are known connections that I alluded to earlier in this talk between notions of stability of a learning algorithm and its ability to generalize. And the stability notions that were considered in prior works do not compose. But differential privacy is stronger, and composition is one of its signal properties. So this gives us a calculus for building up complex algorithms that satisfy stability guarantees that are sufficient to give generalization, even under adaptive analyses. So past work has considered the generalization properties of one-shot learning procedures, but our work, because it gives you this toolkit that you can build things out of while maintaining privacy, shows that differential privacy implies generalization in the adaptive setting and beyond the framework just of classification. Now, people who work with data will say, get out of my way. Down with differential privacy interference. I don't want to interact with the data set in a differentially private way. I didn't want to do it for privacy, and I certainly don't want to do it now. And we want to do things the way we always have done them. And I don't blame data analysts for wanting to do things the way they've always done them. Why should they want to change? Why should anybody want to retrain? My answer is, go ahead, make my day. However, let's look at this in the context of a holdout set. And what I'm going to say is do whatever you want on the training set, but when you access the holdout set, do it in a differentially private way. That's all. So first of all, notice, because you're computer scientists, that playing with the training data and interacting with the holdout set in a differentially private way preserves the privacy and prevents overfitting to the holdout set. Why? Because we know that interacting with the data set in a differentially private way gives you, prevents overfitting. And an algorithm that plays with the training set and then interacts with the holdout set in a differentially private way is just an algorithm that has the training set hardwired into its control. So it's just some other big fat algorithm that's interacting with the holdout set in a privacy-preserving way. So this is the right abstraction. So in a traditional holdout, you learn on the training set. You start with a bunch of data points, you randomly partition them into holdout and training, and you, so that the distributions from which T and H are drawn are the same. You learn on the training set, you check your validity of your conclusions against a holdout set, and this works because since you haven't touched them yet and they were drawn from the same distribution as the training data were, these are just fresh samples from the same distribution. So you're checking that you haven't overfit to your training set. And, oh, sorry, that's what I just said. Okay, so now what? I mean, either way, whether you find that you have overfit or you have not overfit, can you iterate? Can you go back to your training set now and do some more analysis and then go back and check some other conclusions on the holdout set? Well, the holdout set is no longer fresh. Your subsequent questions depend on the holdout set. Okay? That's in a traditional holdout set. And this can lead to overfitting of the holdout set. So in the reusable, you learn on the training set, you check against a holdout via a differentially private mechanism, and that provides useful information about the distribution from which the holdout set was drawn, and therefore also the training set was drawn. But it also ensures that future exploration does not significantly depend on the holdout set. So H stays fresh. Okay, and I would like to stop there. Oh, almost. So here are my conclusions. All right. Private data analysis is a problem that's been studied for at least 50 years. Differential privacy is a solution concept that is quite general, and it's robust to the networked world because it handles arbitrary side information. Also, there is no competing theory of privacy-preserving data analysis. In addition, thinking in terms of differentially private algorithms has taught us things about non-private algorithms. And it also differential privacy tells us something beyond privacy, something that is very fundamental about computing with stability. We don't know all of the implications of these facts. These are very, very new results. But it's a very exciting direction. Whoops. Thank you. Yes?
If I wanted to wreck differential privacy, would I do something like give you jointly dependent statistics? And then would that derail it?
So it wouldn't. So the answer is no, you can't derail it, and none of the, the answer is no, you can't derail it. That there are proofs that say that you can't. But there are limits to what you can do. That fundamental law of information recovery is a fundamental law. It has nothing to do with differential privacy. I told you about it before I mentioned differential privacy. So what it says is that as you ask many questions, you must eventually start making the answers either really noisy or turn off the data set entirely. I mean, you have your choice. Okay. But you can't wreck it.
So the joint independence isn't
not an issue.
absolutely. Okay.
Yeah. Other questions? Yes? Speak up, I'm having trouble. So the question is whether differential privacy is too strong a concept. Certainly we've heard that said. Now, this is a difficult question to answer. If you go back to the fundamental law, there's a set of queries that gives rise to that law. Okay? What differential privacy can do is basically match the bounds from there. So in that sense, it cannot be considered to be too strong. There is still room, though, for particular kinds of queries and particular kinds of data sets where somehow or other you may hope to do better, where we don't necessarily have such tightness and we don't know what the answers are. But you cannot accurately make the general statement that it is too strong. But this does bring up, again, the fact that there is no panacea. So people have big data sets. They want to study them for science. They want to study them for fame. They want to monetize them. And what a principled investigation of privacy shows you is that there are limits on how much these data can be exploited without compromising privacy. So you have to make some choices. I guess I didn't include the slide, but we have a proposal. Deirdre Mulligan and I actually have a proposal for starting to get your hands on this kind of thing, which is to have an epsilon registry that is analogous to a toxic release registry for toxic fumes. So the idea of modeling privacy law on environmental law is not new with us. There are other people who have studied that in the legal literature. But there are a lot of advantages to requiring this registry. Clearly, the people who are using data now are burning through privacy at a great rate. So the first thing that we would want to do is we'd say, okay, pay a fine if epsilon is infinity, because we really want to get them to try. They have to try. Now, the numbers will be horrible, but it would be interesting to at least start having them up there for comparison purposes. So you might like this company better than that company because this company burns through your privacy at a slower rate, forcing an adversary to work harder in order to compromise your privacy. Also, instead of just having sort of the people in the research community trying to figure out what people want to compute on and what they want to compute and how they should do it in a differentially private way, we would hopefully be able to transfer some of the responsibility of doing that to the people who are monetizing the data, who are gaining from the data. So we get their brains involved in it, and they may also have domain information about the data and the kinds of things that they're doing with it that will allow them to avoid the worst case bounds because there's something special about what they're doing. Okay.
I tried hard for privacy reasons. I tried to get both of my neighbors to ask me this question for me, but doesn't everybody have grow lights?
I love living in California. Okay, so let's thank you.